Hello everyone, welcome to the presentation for our conference paper. The title of our paper is When They Go High, We Go Low, Low-Latency Live Streaming in dash.js with LoL. This paper is submitted for one of the challenges organized and sponsored by Twitch for the ACM MMSys 2020 conference. The challenge requires solutions to handle low-latency live streaming. Solutions should be able to keep the latency to around 1 second, while being able to balance the other factors to maximize viewers' quality of experience, commonly known as QoE. Some of these QoE factors include maintaining high video quality, low rebuffering, and low quality switches. The approach that we take here is that we revisit the entire adaptive streaming system and extend some of these selected components that would help us achieve such a low latency performance. Our resulting solution includes these three main components. First, we employ HTTP adaptive streaming in the form of an ABR Selection Module, which allows us to select or switch between ABR algorithms, such as between our Heuristic and Learning-Based ABR, to maximize QoE based on the changing environment. Second, the given system also implements chunk transfer encoding, which helps reduce latency, but introduces a new problem in throughput measurement, which we will discuss further later. Hence, we also implemented a throughput measurement module that allows for more accurate measurements. Finally, we have adaptive playback, which allows us to control the playback speed to maximize QoE. For our solution, we first introduced the QoE model that we use. This model has been adapted for low latency live streaming and is formally written as this equation over here. The key takeaway from this slide is that there are 5 main factors being considered in our model, as shown below. The model rewards for bit rate, which translates to video quality, and penalizes for 4 other factors that negatively affects viewer experience, such as rebuffering, latency, deviations in playback speed, and bitrate switches. Next, recall that we introduced earlier that we have 2 types of ABR algorithms. They are heuristic-based and learning-based. We chose to implement each of these 2 because they are popular categories of ABR algorithms, and they come with different strengths and could perform better under different conditions. Hence, we believe they would serve as good comparisons and potentially good complements in our ABR selection module. Generally speaking, heuristic-based algorithms tend to use fixed heuristics, such as mathematical rules or approximations to determine the next best bit rate to stream at. Whereas learning-based algorithms do not follow fixed heuristics, and instead attempt to learn from changes in the system environment to make decisions based on past data. In the following slides, we introduce in greater detail each of these 2 algorithms. For our heuristic-based algorithm, we built upon the contributions of FastMPC and adapt its approach to fit our low-latency live streaming scenario. The general idea is that we calculate the potential QoE across all available options and then select the one with the highest value. It consists of 3 main steps, and we'll go through them over here. And these steps are repeated each time we need to select the next bitrate. First, we permute all possible options of bitrate selection with a look-ahead window. In this example, with a window of 5 future segments and 3 bitrate representations, namely 200, 600, and 1000 kbps, then the possible options that we permute include those listed in this table. For the second step, we calculate the potential QoE for each of these options. This requires our QoE model as introduced earlier, as well as some additional input data, such as the current buffer level and throughput measurements. For each option, we calculate the expected QoE for each of the 5 factors, and then sum them to get the overall value. And finally, for the third step, we evaluate our options based on these expected QoE values. We simply select the one with the highest value as the next bit rate. For our learning-based algorithm, we adapt from the idea of self-organizing maps, which is generally used as an unsupervised classification algorithm. The general idea is that the neurons would, as the name suggests, self-organize across the feature map, such that each state would be appropriately classified under a certain neuron, which represents a certain label. This neuron is selected as the closest neuron to the state by Euclidean distance on a feature map. The neurons move as the video streams and provides new data points to learn from. I'll explain the high-level intuition of the algorithm here, and further technical details can be found in our paper. We first initialize with 3 neurons, which represent the 3 available bitrate levels in our setup. In the first step, we select the neuron that is currently closest to the optimal state, which is a point on the feature map. This optimal state is determined based on the current throughput, as well as our target latency, buffer, and QoE values. Let's say the optimal state is this state over here with the green outline. Hence, the closest neuron is this leftmost neuron. In the second step, we update the selected neuron to move it closer to the optimal state. This is a standard SOM mapping step to reward the winning neuron, also known as competitive learning. We then retrieve the next segment at the bitrate level represented by this selected neuron. In the third step, after the segment is retrieved and played back, we then update the neurons again to learn from our past decision. We first identify our consequent state based on the current latency, buffer, and QoE values resulting from our selected bitrate, and then move the selected neuron closer to it. For example, let's say our previously selected neuron did not do very well, and the consequent state is in fact very far from our optimal state, like this state over here with the purple outline. Then the neuron will be moved away from the optimal state and would be less likely to be selected in the subsequent cycles. Similar to our heuristic-based ABR, these steps repeat each time we need to select the next bitrate. In selecting a suitable ABR for the job, there are multiple approaches that we propose. For a start, we could select based on how much certainty we have on the system and environment. For example, if the system dynamics are not predictable, or if the QoE model is not clear, then learning-based tends to be better, since we do not need to fix our heuristics, such as the QoE model. Alternatively, if we have multiple ABRs already implemented, as in the case in our paper, we could also conduct extensive experiments to evaluate the performance of both ABRs, which is what we have done in our evaluation section. This approach is somewhat more tedious, like a brute force, but it's also useful now as we begin to explore the idea of ABR selection or ABR switching, because these experiments would help us better understand the strengths of either ABR under different conditions. Then, with this knowledge, we could explore the possibility of dynamically switching between both ABRs based on changing user requirements, media, or environment factors. We hope to explore this direction as part of our future work. Next, we introduce our Playback Control Module. The goal is to adapt the playback speed to reduce latency while not risking rebuffering. For example, too fast of playback speed can quickly bring down the latency, but would also deplete the buffer very quickly and risk rebuffering. Here, we use a heuristic-based approach with configurable parameters. This table provides a worked example. First, the system predefines a target latency, safe buffer level, and allowable playback range. And let's say we have these 3 scenarios with different latency and buffer levels. For example, in the first scenario, if the current latency is less than the target latency, then we could slow down the playback, which is good for building up the buffer, so that if the latency starts to grow above the target latency, as seen in scenario 2, then we could speed up the playback to say 1.4 times, so that we can quickly bring the latency down. However, if the buffer is below the safe level, as seen in scenario 3, then we could dampen the speed up to say 1.31 times instead to reduce the impact on rebuffering. Next, we introduce our Throughput measurement module. As mentioned earlier, the use of chunk transfer encoding could help reduce latency for live streaming, but also introduces a problem with existing throughput measurement methods, such as ACT, due to the presence of interchunk idle periods. To visualize this problem, we look at this scenario where the chunks of a segment are generated with idle times in between, such as between chunks 5 and 6. If we were to measure the download time on a segment level from the first to last chunk, such as from B1 to EN, assuming n chunks, and use that segment download time to calculate throughput, then these idle times could erroneously be included and underestimate the actual throughput. To fix this issue, we can see that instead of measuring download time at a segment level, we need to identify the actual chunk download times, as annotated in red over here. Hence, we propose a two-stage algorithm that uses the latest fetch API to improve over act. In the first step, chunk boundary identification, the algorithm identifies the beginning and end times of each chunk download by capturing the move box in the fragmented MP4 data. Thanks to the fetch API, our algorithm is able to use the streaming response body object, which allows us to track the progress of chunk downloads and parse the chunk payloads in real time. In the second step, idle period filtering, we then use this chunk timing information to remove the inter-chunk idle periods from the measured download time. We also employ other enhancements such as ignoring the first and last chunks to avoid any transient outliers. We implemented our solution in dash.js and our code is publicly available on GitHub. The code files changed are also listed over here. We also evaluated our solution to answer these two questions. 1. How do heuristic and learning-based algorithms perform at low latency? And 2. Does our throughput measurement module perform well? To answer the first question, we ran multiple automated streaming sessions to derive the average QoE scores for each algorithm under 5 different network profiles provided by the challenge. We show the results for 2 of the network profiles over here. Note that these network profiles emulate challenging network conditions, such as cascading bandwidth that could drop to as low as 200 kbps. Hence, some of these QoE scores could at times drop to negative values. From our experiments, we note that our learning-based ABR tends to achieve higher overall QoE than our heuristic-based, especially for the 2 network profiles here. To understand the performance difference better, we look at the session metrics collected in the table. We can see that the higher QoE score is largely due to the lower number of bitrate switches in learning-based as compared to heuristic-based, which translates to a more stable stream. Intuitively, this is likely because the learning-based algorithm tracks 4 dimensions with 4 different weights, including latency, buffer, and QoE, which makes the algorithm more sensitive to changes in any one of these factors. Hence, it could pick up the bandwidth changes very quickly and allow the stream to better handle sudden bandwidth drops. However, we also note that heuristic-based APR has its own merits in the sense that it could potentially achieve better results on some of these QoE factors, such as rebuffering. So this suggests that different APR algorithms do have their own strengths, and hence having an ABR selection module that could select the best APR based on changing requirements and environment conditions may help us leverage these APRs better. To answer the second question, we also collected the throughput measurements made by our implementation and the dash.js default implementation, and compared them against the true bandwidth values provided to the network simulation tool. This figure on the slide plots the measurements across one sample run for each network profile. We can see that the dash.js implementation tends to err at high bandwidth regions where chunk transfer encoding enabled transfers are more likely to occur. This follows our earlier discussion on how CTE may cause issues in existing throughput measurement methods. We also calculated the average measurement error using multiple runs across all 5 profiles and found that our implementation could bring the average measurement error down from 253% to 21% of the true value when compared to the dash.js implementation. This marks the end of our presentation. Again, our code is available on GitHub, so please do check it out and feel free to reach out to us if you have any further questions. Thank you.